Hey there, welcome to a video discussing section 9.4, Intro to Parametric Equations. My apologies for not doing this on Friday afternoon, just got a little sidetracked with family stuff. But here it is Saturday morning. Hopefully you guys are having a good start to your weekend, and let's get to the notes. So again, this is on Introduction to Parametric Equations. This is actually something we have talked about during the first unit. If you were to go back to your first notes, I think page 10 here, we talked about writing functions or equations with x in terms of t and y in terms of t, where t is called the parameter. So the reason why we have this is that, like in physics, for example, when you're trying to break things down to their horizontal and vertical components, where x could be like the horizontal distance traveled, y could be the vertical distance traveled, and t could be time, where t is a common variable for both x and y. This could make analyzing such situations easier to do when you could break the situation down to two separate equations. So this is one reason why we have parametric equations. But at its core, it's just two equations, x and y, and x and y are both in terms of the same variable. Usually we call it t or theta or whatever you want. We are going to be talking about theta often as we move on to polar equations and looking at how to, and kind of tying it to trig and how it relates to conic sections, which is something we've done recently. So again, we've seen y equals f of x, y is isolated on one side, y is a function of x, but again, there are many relations which do not represent functions, meaning they don't pass a vertical line test. And in many cases, we can express relations with variables x and y is often more convenient and useful to express relations in parametric form, as I discussed earlier, like in physics with projectile motion, breaking things down to horizontal and vertical components. And that's what we have here, x in terms of t and y in terms of t, or we could do theta or any variable for that matter. And the third variable, we call the parameter. So let's look at an example. So here you're given two parametric equations, x equals t squared minus 4 and y equals 1/2 t. And that's actually just like the example we did a while ago, but let's just do it again. So sketch the curve where t is between -2 and 3 by making a chart and plotting the points, and will y be a function of x? Then we're going to do some algebra in part B. We're going to eliminate the parameter, and then we'll do another example on the next page, another example on the page after. And it's only 3 pages of notes, so hopefully this video doesn't take more than about, excuse me, 12 to 15 minutes. And just at the same time, I'm also keeping an eye on my 1-year-old who's wreaking havoc in the living room here. So I may have to pause the video from time to time. And actually, if you do want to get a quick glimpse of her, say hi for the camera. Okay. All right. So let's come back and you can see my hair is all messy. It's Saturday morning. All right. Oh no. All right. So anyway, so here's what I'm going to do. I'm going to make a table of 3 columns. Actually, let me take that back. I'll put t, x, and y. So I'll let t be -2, -1, 0, 1. I need more space. Let's do this again. Let's do it over here. So -2, -1, 0, 1, 2, and 3. So we'll start with y because that's easier. You get -1, -1/2, 0, 1/2, 1, and 3/2. Cool. Now let's do it for x. You should get 0, -3, -4, back to -3, back to 0, and in this case, 5. And then just plot the points. So these are the points we have. So 0, -1, which is right here, -3 and -1/2 right here, -4, 0 is right there, 3 -1/2 right here, 0, 1. Hold on. Is that right? Sorry, 2, 1. Hold on, why am I messing up here? Give me one sec, guys. Sorry. So let me make sure I do this right. If I plug in -2, I get 0. Plug in -1, I get -3. Plug in 0, I get -4. Plug in 1, -3. 2, 0. Okay, that makes sense. And then 3, I get 5. If I plug in for y, -1, -1/2, 0. Yeah, okay. I got this. So 0, -1, -3, -1/2, -4, 0. 3/2. That's why I was confused. Got it. 3/2. Oh, -3/2. Yikes. There we go. Okay. So you're probably wondering why I'm losing my mind. Again, I'm also keeping an eye on my daughter too. So 0, 1. Okay, there we go. And 5/3. I know I can do this. Okay, it's a sideways parabola. There we go. You're not going to draw arrows because it does stop at those places. So the answer is no. It's not a function of x, right? It fails vertical line test. Now, let's eliminate the parameter. Now, we expect, because we've talked about conic sections, we expect something that looks like this, right? Y minus k squared equals 4p x minus h, like a sideways parabola. So it's tying closer to what we've been talking about recently, right? So when you have to eliminate the parameter, what you really want to do is do substitution. So we can say t equals 2y. So t equals 2y. And substitute it. X equals, oh god, my short-term memory is terrible. What was it again? Is x equals t squared minus 4. There we go. T squared minus 4. So t squared minus 4 or 2y squared minus 4. So x equals 4y squared minus 4. Or if you move things around like this, so x equals take out the 4. Actually, that's not how we want to do it. You want to move the 4 over. So you can think of it like this, x plus 4 So in this case, your vertex is at -4, 0, which is what we saw. And if you were to find, say, the focus or the directrix, 4p equals 1/4. So p is 1/16. If you want to find those things, you could. But yeah, that's what we actually, hold on a sec. I put the 4p. No, I had it in the right place. That's correct. There we go. So anyway, that's what's happening there. Hopefully that all makes sense. And again, if you go back to that little formula sheet that I shared with you guys regarding conic sections, I think it's right here in my Algebra 2 Trig Honors folder. Spring semester, should be ever, no, I did it in the fall of that year. Yeah, there we go, formulas. Yeah, you can see the 4p is next to x minus h. So in this case, our p is 1/16, opening to the right. So if you want to find directrix and focus, you could if you wanted to, but we won't do that for this case. Okay, cool. Let's keep on moving. Well, hold on. It says, how does this graph this equation different than the graph in part A? Well, obviously it's x, y in terms of x, or the other way around. And what information could be provided so the graph is going to match the one in part A? Well, definitely a restricted domain, but we'll just move on. Okay, so moving on to the notes, let's go to page 2. We'll do the same thing again. So we got these parametric equations, and the set of real numbers was the domain of t. Well, clearly, t has to be positive, right? Cannot be, or 0. So it would be 0 to infinity if we write interval notation. Using answer in part A, construct a table of at least 5 t values. So let's do a 3-column table. We'll do 0, 1, 2, 3, 4. Actually, let's do something with perfect squares. 0, 1, 4, 9, and 16. So plug in 0, get 0, 1, 2, 3, and 4. That's easy. For y, so do 2 minus the t value. So 2, 1, -2, -7, and -14. Okay. Plot the points. So 0, 2, 1, 1, 2, -2, 3, -7, way down here. That's even further down below. So it looks like it's half a parabola pointing down. That's what it looks like to us. Half a parabola pointing down. Let's eliminate the parameter. Graph which you got parts has curve different than the one that you got in part B. Using a realization for stick domain of X, blah, blah, blah. Okay. So let's go through the motions here. So again, 2 minus t and root t. So here we go. X equals root t. Y equals 2 minus t. So you could probably say t equals x squared, right? So y equals 2 minus x squared. And that makes sense because it's pointing down, negative x squared plus 2, a vertical shift of 2 up. And if you were to graph it in its all its glory, it would look like this, right? So the graph is done, the equation's done. How does it differ? It's a full parabola here. If you want to restrict the domain, you'd say x is greater than or equal to 0, which is true because if you let x equal root t and t are greater than or equal to 0, then of course x is greater than or equal to 0, right? Plus, how can a radical be negative if you don't have a negative out in front of it, right? Outputs of radicals are always going to be positive. So that's that one. That should be pretty easy. And the last one here. And then we're done. And I'll just have to clean up the mess my daughter made here in the living room. Good thing my wife's not home. Anyway. Let's see here. So consider the parametric equation, blah, blah, blah. X is root t minus 3, y equals t cubed. So again, the domain is going to be t is greater than or equal to 0 once again. We'll make a 3-column table. See here. We'll do 0, 1, 4, 9, and 16 again. So for x, you should get -3, -2, -1, 0. That comes out nicely. And 1. Look at that. And then for t cubed, ooh, those are going to be big. 0, 1, 64. Yikes. 729. And I'm not going to attempt to do that one. Just a large number. So -3 comes 0. -2 comes 1. -1 comes 64. Ooh, yikes. Look at that. 0 comes 720. Way up there. So it's almost like it's exponential in a way, it seems. That's what it kind of seems like we got ourselves here. Again, let me rewrite those equations because I'm pretty sure the next person asks us to eliminate the parameter, which means get rid of t. Yep, let's eliminate the parameter, draw the full curve, and just see how things are different. And of course, restrict the domain on the equation in terms of y and x. So again, I'll probably get t by itself in the x equation. That might make the most sense. So x plus 3 equals root t. T equals x plus 3 squared. So y will be x plus 3 squared, then cubed. So actually, it's not exponential, it's just a crazy polynomial. X plus 3 raised to the 6th power. And yeah, that's what we got for that one. So if I were to graph that, clear that there's a point -3 comma 0. Let me erase this previous graph. Yeah, let's do it. So -3 comma 0. And if I were to plug in -1, obviously I would get 4. -2, I get 1. 0, sorry, no, if I get plug in -1, I get 2 to the 6th power, 64. Yeah, so sorry. -2 is 1. That's way up here. And 0 is way up here. I'm guessing it would look like this. It kind of looked like a parabola in some ways. Given the end behavior, if x were very negative, it's still positive. So, and actually, this will never be negative because the range will never be negative because you're raising something to an even exponent, and you don't have anything else going on there. Yeah, and if I want to restrict the domain, I would say x is greater than or equal to -3, or -3 bracket infinity. That one. And I think I might have messed up the domain for over here. I think I probably meant to say 0 to infinity. If I made that mistake, my apologies. And that's that. So the video is short, as I promised. So don't worry about part 2. We'll do that in class, but we'll just hit the ground running with part 2 of the notes. That's about 6 pages, looks like. So it's a lot to do, but we have 75-minute classes, so that's all good. And then we'll have let's make sure my dog doesn't choke on that. No, don't need that. Yeah, and I think that is it. And then we'll do the worksheet, and then we'll talk more about conics if you have any questions about it. Remember, we have our conics test, a small conics test on Friday. And again, I see you Tuesday, not Monday. I take it back. I see you guys Tuesday morning on Halloween. Hope you guys are decked out in all your Halloween regalia. And yeah, do you want to say bye? Say bye. Okay. Anyway, I gotta clean up this mess here. All right, I'll see you guys on Tuesday then. Goodbye.